Hello, today we'll discuss about unit number 5 of subject design of machine element 1, in which this unit contains the design of threaded joint and welded joint. So firstly we will see about design of threaded joint. So just we will go with first definition, advantages, disadvantages and various forms of threads. So first we will see about only threaded joint or screwed joint. Threaded joint is also called as a screwed joint, and the next portion will be of welded joint. So first we will go with the definition. What is the threaded joint? A rod which is having the helical groove on the external cylinder surface is called as a screw or a bolt. A hollow rod which is having the helical groove on the internal cylinder surface is called as a nut. As you already know the nut and bolt arrangement, as the nut is having internal threading and bolt is having external threading. So this joint which is formed by using screw or bolt and nut, the joint is called as a screwed or threaded joint. So generally the nut and bolt arrangement is called as a screwed or threaded joint, and it is a temporary joint which is easily dismantled are required. In case of a easily dismantle, we can use the nut and bolt arrangement, and in general V threads are used to joint. Now what are the advantages? The first one, it is convenient to assemble and disassemble. The second one, it is highly reliable in operation. Third one, it is wide range of screwed joint is available. And fourth one, it is relatively cheap for production. And fifth one, it gives high clamping forces. So these are the various advantages of the screwed or the threaded joint. Now disadvantages is that the stress concentration in that thread is very high and the strength is less than the welded joint. So strength is the major issue in of threaded joint, as the strength is very less as compared to the welded joint. Now various forms of threads. Now the first one, Whitworth thread, Acme thread. Third one is a buttress thread. Fourth one is a square thread. Fifth one is a knuckle thread, and sixth one is a unified thread. So these are the various of forms of threads. Now we will see the advantages of V threads over the square thread and disadvantages of the V threads over the square thread. Now the advantages, we will see the first one, the greater frictional resistance to the motion, hence it is suitable for fastening. Then second one, the high strength than the square threads. The third one, the manufacturing easy and cost is low. The fourth one, it is used in a bolts, nuts, studs, tab bolts, etc. The disadvantages of a V threads over the square thread is that the first one, the greater frictional resistance to the motion, hence not suitable for power transmission. And second one, the bursting pressure is maximum on nut. So these are the various advantages and the disadvantages of the V threads over the square threads. Now the terminology of V thread. Here the various terminology we are going to see. The first one is the major diameter. In diagram you can say there is external threading and various terms are related to that particular diagram. So first we will see the major diameter. What is major diameter? It is the largest diameter of an internal or external screw thread, and it is also called as nominal diameter. As already in unit number 4, in case of a power screw, we have already seen that nominal diameter, core diameter and the what you can say, the major diameter. So all these three terms we have already seen in a unit number 4 of power screw. So what is minor diameter? Now it is the smallest diameter of an internal or external screw thread, and it is also called as core diameter. And then third one is a pitch circle diameter, and it is the imaginary diameter which is passing through the mean of major and minor diameter. Then fourth terminology, pitch. In case of a power screw, already we have seen that pitch, that is small p notation. And what is p? It is the distance between two successive threads in case of a power screw. But in case of this one, it is the distance between a point on one thread to the corresponding point on next adjacent thread, the same as it is in case of a power screw, the same, the successive distance between the two threads. And pitch is nothing but pitch is equal to 1 divided by number of threads per unit length of the screw. The fifth one, lead. It is the distance through which a screw advances axially in one rotation of the nut, where lead is equal to number of starts into pitch. So the most of the terms are from the unit number 4, that is from power screw, as we have already seen that detail. You can also refer my unit number 4 videos for this one. Now the sixth one, the right hand threads. Now when the nut assembled on the screw is given clockwise rotation leading to the tightening of the joint, then thread is called as a right hand thread, as shown in figure. As we already seen right hand and left hand thread. What is right hand? If the thread is in direction from left to the right, but it is in upward direction, is called as a right hand thread. And if the direction of the thread is from the left to the right but in a downward direction, is called as a left hand thread. So when the nut assembled on the screw is given clockwise rotation leading to the loosening of the joint, then thread is called as a left handed thread, as shown in figure. Now the various types of screw fastening. The first type is of throw bolt, tab bolt and the stud. Now trap bolt is what? It is the cylindrical bar with thread at one end for nut and head at the other end. The cylinder part is known as a shank. In first diagram you can see the measure of the portion is not threaded. Now tab bolt, it is the cylindrical bar with threads over entire length and screwed into tapped hole for fastening. And now the third one, stud, it is the cylindrical bar with threads at both ends. One end is screwed into tapped hole and other end is for the nut for fastening. So these are the three types of the screw fastening. Now the various types of a screw fastening. The first one is rounded head. You can see the upper head of that particular screw is rounded one. Then pan head, philister head, oval head and flat countersunk head. So these are the various types of a screw fastening. Now the fourth type of a screw is a cap screw. It is similar to a tab bolt. It is screwed into a tapped hole of one of the parts to be fastened without nut, and they are of small size. Then fifth one is a set screw. Here in this diagram, three diagrams are shown over here. A set of screw is screwed through a threaded hole in one part so that end of the screw presses against the other part. Now here is the various types of stresses in a screwed fastening due to the static loading. Now that again it is divided into three major types. The initial stresses due to the screwing up forces. The second one, stresses due to external forces. And third one, stresses due to combination of stresses at initial stresses and external forces. Now that initial stresses due to screwing up forces, it is again divided into four types. That is tensile stress due to stretching of bolt, torsional shear stress across threads and compression or crushing stress. Then the stresses due to external forces is again of three types. That is tensile stress, shear stress, combined tensile and shear stress. And the third one is a stresses due to the combination of stresses and initial stresses and external forces. Now we will see one by one the stresses. The initial stress is due to screwing up the forces. Now the first one, the tensile stress due to the stretching of the bolt. The initial stresses in a screw fastening are not accurately determined. Therefore, bolts are designed on the basis of direct stress by considering large factor of safety. The initial tension in a bolt based on experiment may be found by empirical equations. Now in these formulas all the empirical relations are used and which are standard one. Now the A1, the fluid tight joint, which is of Pi or P1 is equal to 2840 times D0, where Pi or P1 is the initial, Pi is the initial tension in a bolt, and where D0 is the nominal diameter of the bolt or the major diameter you can say. So the diameter M16 or M18 are not permitted for fluid tight joints. Now non-fluid tight joints is what? Pi or Pi should be 1420 times of a D0. Now the C, the bolt without initial stress, where P is equal to delta into A, where the stresses area for the initial tensile stress may be determined by the equation, that is stress area is equal to pi by 4 dP plus dC by 2 bracket square. So by using this formula you can find out the stress area. Now the second one, the torsional shear stress due to the frictional resistance of threads during its tightening, where Q is equal to 16 into T divided by pi into dC cube. Where third one, the shear stress across threads, where Q of screw, if Q is nothing but the shear stress, is equal to P upon pi into dc into n into t, where Q, that is shear stress in a nut, is equal to P into pi into d0 into n into t. Now the fourth one, the compressive or crushing stress. Now that sigma Ck is the for compressive or crushing is equal to P upon pi by 4 d0 minus d0 square minus dc square into n. Now the stresses due to the external forces, the first one is the tensile stress and it is denoted by sigma of t, which is equal to P2 divided by pi by 4 dc square. Where if the external load taken by the number of bolts, then you need to multiply that denominator with the n, that is n is the number of bolts. So the formula will become sigma t is equal to P2 upon pi by 4 dc square into n. Now the second term, shear stress. The shear stresses may be induced in a bolt on its shank, not on the threaded portion. So the Q is equal to PS divided by pi by 4 d0 square into n. Now the third one, the combined tensile and shear stress. Now in that again maximum principal shear stress and maximum principal tensile stress. So maximum principal shear stress Q max is equal to 1 by 2 square root of sigma t bracket square plus 4q square, where maximum principal tensile stress sigma t is equal to 1 by 2 sigma t plus 1 by 2 square root of sigma t square plus 4q square. Now the stresses due to combined forces. The resultant axial load on a bolt depends upon the following factors. The first one, the initial tension due to tightening of the bolt. The second one, external load, and third one, relative elastic yielding, that is springiness of the bolt and connected member. So the stresses due to these combined forces. Now when the connected members are very yielding as compared with the bolt, which is of a soft gasket as shown in figure here, in the bolt and that particular two plates the gaskets are used, and the resultant load on the bolt is approximately equal to the sum of the initial tension and the external load. Now when the bolt is very yielding as compared with the connected member as shown in earlier figure, then the resultant load will be either the initial tension or the external load, whichever is a greater. So the resultant load P on the bolt, that is P is equal to P1 plus A upon 1 plus A into P2, where P is equal to P1 plus K is nothing but A upon 1 plus A into P2, where P1 is what? Initial tension due to tightening of the bolt, that is 2840D0, where P2 is equal to external load on the bolt, where A is the ratio of elasticity of connected parts to the elasticity of a bolt, and for soft gasket and large bolt the value of A is higher and K is approximately equal to the 1. Here in this table the K values are given as per the type of joint, but for the hard gasket or metal to metal contact surface the value of A is small and the resultant load is mainly due to the initial tension. So here according to the type of joint the K value are already standardized. The first one is metal to metal joint with a trough bolt, so there is 0 to 0.1 value. Hard copper gasket with long trough bolt 0.2 to 0.50. Then soft copper gasket with long trough bolt 0.50 to 0.75. Then soft packing with trough bolt 0.75 to 1, and soft packing with studs is the value of K is a 1. Now the most important concept is bolts of uniform strength. Now here we will see when an ordinary bolt as shown in figure A, here the three diagrams are given A, B, C, where the A is called as the ordinary bolt. When it is subjected to the shock loads, the stress concentration occurs at a weakest area of a bolt, such as a core diameter of the threaded length of the bolt. So in this case the magnitude of stress is maximum at core diameter than the shank. The unthreaded portion is called as the shank and the threaded portion is called, means what, the area is removed from that particular bolt, so that whatever the threaded portion is called as the weakest part. So when it is comes under the shock loads, the weak portion will take the maximum stress, and because of the weakest part the failure may take place at that weakest part. If the shank diameter of the bolt is turned down to a diameter equal to a slightly lesser than the core diameter as shown in figure B, if you see that the shank diameter is lesser than that core diameter, then shank of the bolt undergo a higher stresses. Thus, the shank will absorb a large portion of the energy, and the bolt in this way becomes stronger and lighter, and it increases the shock absorbing capacity of the bolt. So, because of the increased modulus of resilience, this gives bolt of uniform strength. So, the resilience of the bolt may increasing its length. So, the second alternative method to obtain the uniform strength as shown in figure C. In this method, an axial hole is drilled through the head as far as threaded portion such as area of shank becomes equal to the area of the root area of the thread. So according to these three diagrams, one first A diagram, it may breaks easily, but in case of if you reduce the diameter of the shank, or you can take a hole in that particular bolt and you can observe the bolts of uniform strength. Now the uniform strength of the bolt can be written as pi by 4 into d1 square is equal to pi by 4 into d0 square minus dc square, where d1 square is equal to d0 square minus dc square, where d1 is equal to square root of d0 square minus dc square, where what is d1? d1 is the diameter of the hole, d0 is the nominal diameter of thread, and dc is the core diameter of the thread. Now the design of a bolts for the cylinder cover or cylinder flange, you can say. Upward force acting on the cylinder cover. First we will see how much will be the force acting on that cylinder cover. So Pn is equal to pi by 4 into d square into p. So by using that formula, you can find out the normal force on that particular cover, where n indicates normal force on cover, where d, capital D, is the diameter of the cover and p is the pressure on cylinder. And this force is taken up by n number of bolts. So p is equal to Pn divided by n. If there are number of bolts, you have to divide that normal force with the number of bolts. Now the tensile stresses in each bolt, where sigma t is equal to p upon pi by 4 into dc square. Usually the size of the bolt for safe design is 16 to 24 mm, and this value is assumed, and accordingly number of bolts are calculated. So by using that formula, you can find out the tensile stress or sigma t. Then third one, the pitch circle diameter of bolt, where dp is equal to d plus 2t plus 3d1, where dp is equal to pitch circle diameter of bolt, where d1 is equal to diameter of hole, and which is equal to d0 plus 1, where t is equal to thickness of the cylinder cover, and which is of 10 mm. Now the fourth one, the circumferential pitch, where pc is equal to pi into dp divided by n, where check whether pc lies between 20 square root of d1 to 30 square root of d1. If yes, then assumptions made in tensile stress are correct. So as there are the empirical relations and the assumptions, so we need to follow these empirical relations and assumptions while designing any particular threaded joint. So the design of a bolted joint subjected to the eccentric loading. In the eccentric loading of bolted joint, design the dimensions of the bolts. The design of bolts is done by the following two cases when eccentric load is there. The first case is parallel to the axis of the bolt, and second one is the perpendicular to the axis of the bolt. Now first we will see the bolted joint subjected to the eccentric loading acting parallel to the axis of the bolt, and second type is the perpendicular to the axis of the bolt. Now here is W is what? The load which is acting. In diagram you can see the W which is acting parallel to the axis of the bolt. So here we will see the each bolt is subjected to the direct tensile load. So WT1 is equal to W divided by N, where N is the number of bolt used in the joint and the load W, which tends to rotate the bracket about the edge AA. AA section is taken. You can see it in diagram. Let W be the load in a bolt per unit distance due to the turning effect of a bracket, and let W1 and W2 be the loads on each bolt at a distance L1 and L2 from tilting edge AA. Therefore, load on each bolt at a distance L1 is W1 is equal to small w into L1. Similarly, load on each bolt at a distance L2 is equal to W2 into W into L2. So W1 and W2, these are what? The loads on each bolt, where small w be the load in bolt per unit distance. Now also moments of these loads about tilting edge AA is M1 is equal to W1 into L1 according to the mechanics, and as you already learned, taking moments about anything, that is distance into perpendicular load. Now M1 is equal to W into L1 into L1, where M1 is equal to W into L1 square. Similarly, M2 is equal to W into L2 square. Now the moment of the load acting on a bracket producing the moment about the edge A, which is given by M is equal to W into L. Now according to the Wagner's theorem, M is equal to N1 into M1 plus N2 into M2, where N1 is what? Number of bolts at a distance L1, where N2 is what? Number of bolts at distance L2. So again we will rearrange the term. We will put that M is equal to W into L in that equation. So we will get W into L is equal to N1 into M1 is what? W into L1 square plus N2 into M2 is what? W into L2 square. So for uniform strength of the bracket joint, even number of bolts are used, that is N1 is equal to N2. Hence above equation becomes W into L is equal to N1 into W into L1 square plus L2 square. Now so W is equal to, small w is equal to W into L divided by N1 plus L1 square plus L2 square. So the most heavily loaded bolts are those which are situated at a greatest distance from tilting edge. So here bolt at a distance L2 are the most heavily loaded bolts. Therefore tensile load on each bolt at a distance L2 is WT2 is equal to W2 into W into L2, where WT2 is equal to W into L into L2 divided by N1 into L1 square plus L2 square. So the tensile load on most heavily loaded bolt is WT is equal to WT1 plus WT2. As already we have find out WT1 and WT2, so just we have to add the to find out the total WT. So the tensile stress induced in the bolt is sigma T, already we have seen, is equal to WT divided by pi by 4 DC square. So from above equation core diameter may be obtained here. So from this equation DC you can find out. Now the next term, the bolted joint subjected to the eccentric load acting perpendicular to the axis of the bolt. Earlier we have seen the bolted joint subjected to the parallel to the axis of the bolt. Now here is the eccentric load acting perpendicular to the axis of the bolt. Now here is 4 bolts are attached on which plate is there, and the W is acting at the free end of that particular bracket. Now here each bolt is subjected to the direct shear load of Ws is equal to W upon N, where N is what? The number of bolts used in a bracket. So eccentric load W will try to tilt the bracket in the clockwise direction about edge AA, and bolt will be subjected to a tensile stress due to turning movement. So the maximum tensile load on a heavily loaded bolt may be obtained as WT is equal to W into L2, as already you have known W into L2. Now WT is equal to W into L into L2 divided by N1 into L1 square plus L2 square. When the bolts are subjected to the shear as well as tensile load, then equivalent load may be determined by WT is equal to WT by 2 plus 1 by 2 square root of WT square plus 4WS square, where WSC is equal to 1 by 2 square root of WT square plus 4WS square. So WT is the tensile load and WSC is the shear load. So the dimensions of the bolt may be determined as sigma T is equal to WTE divided by pi by 4 DC square, where Q is shear stress is equal to W into SC, shear stress due to eccentric load divided by pi by 4 into DC square. So these two types are the most important, then the problem will be based on these two types. So you need to remember these formulas related to the eccentric load parallel to the axis of the bolt and the eccentric load acting perpendicular to the axis of the bolt. Thank you. Now in next video we will see the screwed or the design of a welded joint, that we will see in a next video.